Hello students. In this video we're going to solve a 2x2 system of equations using Cramer's rule. So the first thing I'm going to do is I'm going to write this 2x2 system as a matrix equation. So I'm going to highlight the coefficients on the left hand side and the resulting vector from the right hand side. I'm just going to pick out those coefficients, and then I'm just going to write it as a linear combination on the left hand side. And remember, at this point we're asking the question, how can we write the vector 5, 4 as a linear combination of the columns of this matrix 2, 3, 1, 2. Okay. So again, I'll say that. How can we write this vector 5, 4 as a linear combination of the vector 2, 3, and 1, 2? So geometrically, what's occurring here is that, here's the vector 1, 2, here's the vector 2, 3, and here's the vector 5, 4. Now these vectors, remember from the parallelogram law, they'll make a parallelogram. But we want this vector to be the diagonal of that parallelogram, and it's not going to do that unless we somehow rescale and alter these vectors. So we're going to rescale and change their direction, is what we're going to do. So we're going to make this vector longer, we're going to change the direction of this vector, and we're going to get an image that's going to look like this. And then the result will be, when we finish making the legs of the parallelogram, is that by stretching this vector out, by stretching and changing direction of this vector, when we connect the legs of the parallelogram, they become the blue vector becomes the diagonal of the parallelogram. So what are those scale factors? What are those scale factors that convert this vector and this vector into this vector and this vector? Cramer's rule will help us determine what those scale factors are. So I'm going to finish writing this as a matrix equation, and then here comes Cramer's rule. We're going to take the area of this parallelogram down here. So in other words, that is the area of this parallelogram created by the red vectors. If I were to draw another leg out this way and draw a vector parallel to this one and then a vector parallel to this one, then we'd get a parallelogram. We're going to scale both areas with, we're going to scale each factor by that respective area. Then Cramer's rule goes on to tell us that if we take the right hand side, the vector 5, 4, and since this is the variable x1 that comes from the first column, replace the first column of the numerator by the right hand side. And since x2 corresponds to the second column, we're going to put 5, 4 in column 2 of the numerator. And then what do we do with the remaining columns? Well, you just leave them alone for x1. The second column will be left alone. For x2, the first column will be left alone. So I'll repeat that. Cramer's rule says to take the determinant of the right hand side and make that the denominator. For the numerator, replace, if it's x1, replace the first column by the right hand side, leave the second column alone. For x2, leave the first column alone and replace column 2 by the right hand side. Now you just have to make the computations. So the determinant of the numerator here is 5 times 2 minus 4, so that's 10 minus 4. The bottom is 2 times 2, which is 4, minus 3 times 1, which is 3, so 4 minus 3. And likewise, for x2, it's going to be 2 times 4 is 8, minus 5 times 3 is 15. And then the denominator will be the same as in the previous case. You do those calculations, you'll get a ratio of areas 6 to 1 and minus 7 to 1. And so the scale factors turn out to be 6 and minus 7. So what this is telling us is this linear combination here. If we scale the vector 2, 3 by 6, so if we take this vector 2, 3 here, if we multiply it by 6 and stretch it out, we're going to get a vector 12, 18. So that's stretching the vector 2, 3. If we take the vector 1, 2 and we stretch it by minus 7, So we're going to take this vector 1, 2 here, and we're going to stretch it by -7. So that means minus, we're going to go in the opposite direction. And then we're going to get -7 minus 14. Then if we do that, the right-hand side will be the diagonal of this parallelogram created by these stretched and rescaled vectors. So that's how we find the scale factors to make this linear combination work to give us the right-hand side. And you could double check the arithmetic. 6 times 2 is 12, -7 times 1 is -7, 12 minus 7 is 5, 6 times 3 is 18, -7 times 2 is -14, 18 minus 14 is 4. Okay, good luck.